question 5 is all about electricity and circuits and understanding different elements and different properties of circuits, starting with what is meant by the electromotive force. So the most important thing to remember when dealing with EMF is the word force is deceptive. It is not actually a force, it is energy. And specifically, it is energy given per unit charge. So it's the number of joules carried by each coulomb. Or if you like the truck model, it's the coal carried by each of the little trucks. But it's a 2-mark question, so it's not enough to just say it's the energy given to each unit charge, but also it is therefore what drives charge in a circuit, right? Because without this energy, charge wouldn't have the kinetic energy required in order for it to flow around the circuit. So we want to add that to our explanation for a 2nd mark. But to drive charge around the circuit. So something along those lines, but do be mindful of the word energy. In this case, it was not underlined, but there have been previous papers where it is, so you definitely want to focus on the energy element of it rather than pushing or like force elements of it, because it's not a force, right? The unit of it is volt, which is joules per coulomb. There is no newtons in there anywhere. Then we have a circuit. This circuit has 2 heaters and a motor, and then different switches that either activate none, both, or all, just one of the heaters, depending on your setup. So for this particular setup, we only have S1 closed and S2, but not S3. So that means R2 is currently not having any effect on our circuit. My current either goes through R1 or it goes through the motor, and that's it. So question I is asking me to calculate the current in R1. So to do that, I want to identify all of the things that I know are happening in R1. So I'm told the resistance, which is useful. And I'm not told much else about R1, but I am told that the EMF is 240, and this is a parallel circuit, so that means that 240 volts are given to me by my battery or by my power source, and R1 is the only load on that circuit that it's on, or in that path, or in that branch. Therefore, the full 240 volts given to it by the main supply have to be used at R1. So if I know my potential difference and I know my resistance, then I can very easily calculate my current using Ohm's law. So I write it down, I put in what I know, divide both sides by 30, and I get a current of 8 unit amps. Now I want to find the power. Multiple ways to find the power. The most obvious equation, I think, is PV times I, and that's actually the equation that the mark scheme prefers. So we use 240 times 8 amps, and so you end up with a power of 1900, I forget the unit here, is watts. If you got stuck in part I and now you know you need the current, but you're like super stuck, there are other formulas that you don't need to know, but you can still probably use. For example, this one here, which is literally just, instead of writing I, we write I as V over R, which comes from Ohm's law. So that's fine, but I feel like if you can get to that point, you could probably do part I. And then we are told about R2, so things are changing a little bit because now switch 2 and 3 are closed. And it's asking us to compare the current that is now going to start flowing through R2 and how it's different to that of R1. So the key thing here is that my resistance in R2 is different than in R1. And in fact, it's not just different, it's much larger, and it's larger by a factor of 2. So resistance and current are inversely proportional because resistance makes it harder for current to pass through, so less current will. However, it's a linear proportionality based on Ohm's law, so that means if my resistance is 2 times bigger, then my current is going to be 2 times smaller. So since R2 has a larger resistance, then that means that I2 is going to be 2 times smaller than I1. This is bigger. So it's going to be 4 amps essentially. So if here we have I1 that was 8 amps, then I2 is going to be 4 amps, half as much because there's twice as much resistance. So the marks there come from identifying that it's half the size and that the reason for it is because of this inverse proportionality between resistance and current. Then the next bit, we are told that the current in the motor is 0.1 amps. So I'm just going to add that to my diagram so I can keep track of all of this information. So now I know all of the current running through each of my 3 branches, which means I can actually figure out my total current, which is going to be 8 plus 4 plus 0.1, which is 12.1 amps. And why is that important? Well, let's keep reading. We have a cable from the electric heater to the plug for the main socket, and it is safe as long as my current is less than 20 amps. So what should I choose as a safety rating for my fuse and why? So remember that a fuse should break before you reach your maximum current. So if my maximum current is 20, then a safe fuse should be rated less than 19 amps. However, I know from my circuit that my total current is 12.1 amps. So that means I need to at least be able to withstand 13 amps. Like 12 is too little, so I need it to be at least 13 amps. It needs to be somewhere between those two numbers. And again, the reason being I have 12.1 amps that need to flow through, and then the max current is 20 amps. So I don't want to either surpass my maximum or be too low that I can't actually run the current I need.